engineering materials. Engineering materials are mainly classified as metals and non-metals. Metals are and their alloys are iron, steel, copper, aluminum. These things are metals and their alloys. Non-metals are glass, rubber, plastic. All these things are non-metals. Within metals, we are having further classification: ferrous metals and non-ferrous metals. So ferrous metals are those which have iron as their main constituent. So examples are cast iron, wrought iron, steel. And non-ferrous metals are those which have metal other than iron as their main constituent. Copper, aluminum, brass, tin, zinc. All these things are examples for non-metals. For engineering purposes, the selection of a material is very important thing. A selection of proper material for engineering purpose is one of the very difficult problem for any designer. So the best material is one which serves the desired objective at the minimum cost. So when selecting the material, following factors should be considered: availability of material. Second one is the suitability of the material for the working condition or for the service. And third one is the cost of the material. The important properties which determine the utility of the material are physical properties, chemical properties, and mechanical properties. So we will see the different properties now. First, the physical properties of metals. Physical properties include the luster, color, size, shape, density, electric conductivity and thermal conductivity, and also melting point. Then mechanical properties. The mechanical properties of the metal are those which are associated with the ability of the material to resist mechanical forces and load. So these mechanical properties are examples are strength, stiffness, elasticity, plasticity, ductility, brittleness, malleability, toughness, resilience, creep, and hardness. So we will see meaning of each property one by one. First, strength. Strength means it is the ability of the material to resist externally applied forces without breaking or yielding. The internal resistance offered by a part to externally applied force is called stress. The next one is stiffness. Stiffness is the ability of the material to resist deformation under stress. So the modulus of elasticity is a measure of stiffness. Third one is elasticity. Elasticity is the property of a material to regain its original shape after deformation when the external force are removed. This property is desirable for materials used in tools and machines. Steel is more elastic than rubber. Plasticity. Next one is plasticity. It is a property of the material which retains the deformation produced under load permanently. This property of the material is necessary for forgings, for stamping images on coins, and for ornamental work. Next property is ductility. It is a property of the material enabling it to be drawn into wire with the application of tensile forces. A ductile material must be both strong as well as plastic. The ductility is usually measured in terms of percentage elongation and percentage reduction in area. The ductile material commonly used in engineering practice are mild steel, copper, aluminum, nickel, zinc, tin, and lead. Next property is brittleness. It is a property of material to oppose. It is opposite to ductility. It is the property of breaking of a material with little permanent distortion. So brittle materials, when they are subjected to tensile load, they snap off without giving any sensible elongation. Example is cast iron. Cast iron is a very brittle material. Next property is malleability. It is the special case of ductility which permits material to be rolled or hammered into thin sheets. A malleable material should be plastic, but it is not essential to be strong. A malleable material commonly used in engineering practice are lead, soft steel, wrought iron, copper, and aluminum. The next property is toughness. Toughness is the property of material to resist fracture due to high impact load like hammer blows. So toughness of the material decreases when it is heated. It is measured by the amount of energy that a unit volume of material has absorbed after being stressed up to the point of fracture. This property is desirable in parts subjected to shock loads and impact loads. Next property is machinability. Machinability is the property of material which refers to the relative ease with which the material can be cut. So machinability of material can be measured in the number of ways, such as, for example, comparing the tool life of cutting different materials, or thrust required to remove the material at some given rate, or energy required to remove a unit volume of material like that. The brass can be easily machined than steel because brass is a softer material. Next property is resilience. It is a property of material to absorb energy and to resist shock and impact load. It is measured by the amount of energy absorbed per unit volume within elastic limit. This property is essential for spring materials. The next property is creep. When the part is subjected to a constant stress at high temperature for a long period of time, it will undergo a slow and a permanent deformation called creep. This property is considered in designing IC engines, boilers, turbines, like that. The next property is fatigue. When a material is subjected to repeated stresses, it fails at stresses below the yield point stress. Such type of failure of material is known as fatigue. This failure is caused by means of progressive crack formation, which are usually fine and microscopic in size. This property is considered in designing shafts, connecting rods, springs, gears, etc. Next property is hardness. It is a very important property of metal and it has wide variety of meanings. It embraces many different properties such as resistance to wear, scratching, deformation, and machinability. It also means the ability of metal to cut another metal. Hardness is usually expressed in numbers which are dependent on the method of making the test. The hardness of metal may be determined by different tests like Brinell hardness test, Rockwell hardness test, Vickers hardness test, Shor's scleroscope, like that. Next, we are going to see the difference between the different types of ferrous metals. Ferrous metals are those which have iron as their main constituent. The ferrous metals commonly used in engineering practice are cast iron, wrought iron, steel, alloy steels, like that. The principal raw material for all ferrous metals is something called pig iron, which is obtained by smelting iron ore with coke and limestone in a blast furnace. Next one is cast iron. Cast iron is obtained by remelting pig iron with coke and limestone in a furnace known as cupola furnace. It is an alloy of iron and carbon. The carbon content in cast iron varies from 1.7% to 4.5%. This cast iron also contains small amounts of silicon, manganese, phosphorus, and sulfur. The carbon in a cast iron is present in two different forms. One is free carbon or graphite. The other one is combined carbon or cementite. Now, since cast iron is a brittle material, it cannot be used in those parts machines which are subjected to shock load. The properties of cast iron which make it valuable material for engineering purpose are low cost, good casting characteristics, high compressive strength, wear resistance, and excellent machinability. And cast iron, we are having different types of cast irons. First one is called grey cast iron. It is an ordinary commercial iron. It is having a grey color due to the fact that the carbon is present in the form of free graphite. It has a low tensile strength, high compressive strength, and no ductility. It can be easily machined, and also a very good property of cast iron is the free graphite in the structure acts as a lubricant. So because of this reason, it is very suitable for those spots where sliding action is desired. The grey cast iron castings are used for machine tools, automotive cylinder blocks, cylinder heads, housings, flywheels, pipes and pipe fittings, agricultural implements, like that. Next one is called white cast iron. The white cast iron is having a white fracture, and it has no graphite, and whole of the carbon is in the form of carbide known as cementite, which is the hardest constituent of iron. The white cast iron has high tensile strength, low compressive strength, and it is very hard. Therefore, it cannot be machined with ordinary cutting tools, but it requires grinding as a shaping process. The white cast iron may be produced by casting against metal chills or by regulating analysis. The chills are used when the hard and wear resisting surface is desired for products like car wheels, rolls for crushing grains, jaw crusher plates, like that. Next type of cast iron is called a chilled cast iron. It is a white cast iron produced by quick cooling of molten iron. The quick cooling is called chilling, and cast iron produced is called chilled cast iron. All castings are chilled at their own outer skin by contact of the molten iron with the cool sand in the mold. But in most castings, the hardness penetrates to a very small depth,